And now in this lecture we answer two questions. In the first question we find out the area of this green shape, and in the second question we find out the length of this line segment PQ. We find out the length of this line segment PQ that is equals to x. We have to find out the value of x. So we start with the first question. In the drawing we have a semicircle. Actually we have a circle inside this big semicircle. We know that this is line segment AQ, that equals to 4 units in its length. This is line segment TB, that equals to 1 unit in its length. This is angle STB, that is the right angle. And this is angle AQP, that is also right angle. Again, our test is to find out the area of this green shape. So first of all, we will define the radius of this big semicircle as x and the radius of this small circle as y. We define the center of this small circle. This point is point O, and we define the center of this big semicircle. This point is point C. In the next step, we define the point of tendency of tangent AB with this small circle. This point is point N. We define the point of tendency of tangent ST with this small circle. This point is point L. We define the point of tendency of tangent PQ with this small circle. This point is point H. And finally, we define the touching point of the big semicircle with this small circle. This point is point K. In the next step, we join points O and N together by a straight line. Point O is the center of this small circle, point N is the point of the small circle itself, therefore ON is the radius of this small circle, that is equals to y according to our definition. The radius ON that equals to y, the radius ON is drawn to point N, that is the point of tendency of tangent AB with this small circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius NO. If AB is perpendicular to NO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. According to what is given in the question, this is angle PQA, that is the right angle. AB is the diameter of this semicircle, and therefore it is absolutely a straight line. If we focus on the upper side of the straight line AB at point Q, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of AB at point Q? We have this angle that is the right angle, plus this missing angle. In total the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in its size. In the next step, we join points O and H together by a straight line. OH is of course the radius of this small circle is equals to y according to our definition. The radius OH that is equals to y, the radius OH is known to point H, that is the point of tendency of tangent PQ with this small circle. And whenever you have a radius that is known to the point of tendency, then tangent PQ will be perpendicular to the radius HO. If PQ is perpendicular to HO, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule 1. So inside quadrangle HO and Q we have 1, 2, 3 angles. The sum of 3 angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees. According to the rule that the sum of the angles in any quadrangle is equal to 360 degrees. And therefore this fourth missing angle must be equal to 90 degrees in its size. So inside quadrangle HO and Q we have 4 angles. And according to rule 5, any quadrangle that has 4 angles must be a rectangle if not a square. So we relate to quadrangle HO and Q as a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So a rectangle HO and Q, side HO must be equal to the opposite side NQ. But HO is y, therefore NQ, the opposite side NQ must be also equal to y units in its length. And Q equals to y. This is angle STB, this is the right angle. AB is the diameter to the straight line, so if you focus on the upper side of the straight line AB point T, here the sum of the angles must be equal to 180 degrees according to rule 3. So which angles we have the upper side of AB at point T? We have this angle that is the right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we join points O and N together by a straight line. OL is of course the radius of this small circle that is equals to y. The radius OL is equals to y. The radius OL is drawn to point L, that is the point of tendency of tangent ST with this small circle. And whenever your radius is drawn to the point of tendency, then tangent ST will be perpendicular to the radius LO. If ST is perpendicular to LO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to the same rule, rule 1. So inside quadrangle OLTN, we have 1, 2, 3 angles. The sum of 3 angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrangle is equal to 360 degrees. And therefore this fourth missing angle must be equal to 90 degrees in its size. So inside quadrangle OLTN we have 4 angles, and according to rule 5, any quadrangle that has 4 angles must be this rectangle if not a square. So we relate to quadrangle ONTN as a rectangle because it has 4 right angles. So, and we also have the rule that the opposite sides of a rectangle are equal to each other. So rectangle OLTN side OL must be equal to the opposite side TN. But OL is y, therefore the opposite side TN must be also equal to y units in its length. This is line segment QT that is part of the straight line AB. A part of a straight line must be also a straight line, so QT is also a straight line. Therefore QT in total must be equal to y plus y, that is 2y. So QT equals to 2y, I'll write it down. AB is the diameter of this semicircle, and therefore it is equals to 2x. It is twice as long as the radius that is x. AB equals to 2x from one side, but from the other side, AB in total equals to AQ plus QT plus TB. Again, AB in total equals to AQ plus QT plus TB. So I write it down. AB in total equals to AQ plus QT plus TB. So AB in total equals to, or 2x equals to AQ is 4 according to what is given in the question, plus QT. We want to know that QT equals to 2y plus TB. TB equals to 1 unit in its length according to what is given in the question. So in total we should found out that 2x equals to 4 plus 2y plus 1. So 2x equals to 2y and 4 plus 1 is 5. So in total 2x equals to 2y plus 5. Here we subtract 2y from this equation and we get that 2x minus 2y equals to 5. Here we take 2 out as a common factor from those two expressions. So inside the bracket we left with x minus y equals to 5. Here we divide this equation by 2 and finally we get that x minus y equals to 5 over 2. 5 over 2 is 2.5. Again, if we found out that x minus y equals to 2.5. What is the length of this short line segment CN? From the drawing it is very easy to see that CN in total equals to CB minus NT minus TB. Again, CN in total equals to CB minus NT minus TB. So I write it down. CN in total equals to CB minus NT minus TB. So CN in total equals to CB. CB is the radius of the semicircle, that equals to x minus NT equals to y minus TB equals to 1 according to what is given in the question. So in total we found out that CN equals to x minus y minus 1. So CN equals to x minus y. X minus y is 2.5. X minus y is 2.5. Minus 1. 2.5 minus 1 is 1.5. So in total we found out that Cn equals to 1.5 units in its length. This is the missing 97 Cn is equals to 1.5 units in its length. In the drawing we have an internal notch between this small circle and this big semicircle. That is to say they touch each other internally at this point K. Whenever you have an internal notch between two circles or semicircles, you can implement rule 9. So I repeat quickly on rule 9 and we will implement rule 9 in our drawing. According to rule 9, if two circles touch each other internally, then the straight line that connects the centers together passes through their touching points. In the drawing we have two circles. The center of this big circle is here at point O. The center of this small circle is here at point M. And the straight line that connects the centers together is of course the straight line OM. And according to this rule 9, the straight line OM must pass through point P, that is their touching point. Repeat again, the straight line OM must pass through their touching point, that is actually point P. Or OMP is one straight line. Again, according to this rule 9, OMP is one straight line. So we can actually implement rule 9 in our drawing. Well, because in our drawing we have an internal notch between the small circle and the big semicircle at point K. The center of this big semicircle is there at point C. The center of this small circle is there at point O. The straight line that connects their centers together is of course the straight line CO. And according to rule 9, the straight line CO must pass through the touching point, that is point K. So we join point C and O together by straight line. So you can see from the drawing that the straight line CO that connects the centers together in this passes from point K, that is their touching point. Exactly according to rule 9. Or COK is one straight line. Again, COK is one straight line according to rule 9. What is the length of this missing line 7 CO? From the drawing it is very easy to see that CO in total equals to CK minus OK. CO equals to CK minus OK. So I write it down. CO in total equals to CK minus OK. So CO in total equals to CK. What is the definition of line segment CK? Line segment CK starts from point C, that is the center of this big semicircle, and ends at point K, that is the point on the semicircle itself. So this is exactly the definition of a radius. Therefore CK is the radius of this big semicircle, that equals to x according to our definition, minus OK. OK is of course the radius of this small circle, that equals to y. So in total we should find out that CO equals to x minus y. CO equals to x minus y. But we have already found out that x minus y equals to 2.5. Therefore, CO that equals to x minus y is equal to 2.5 units in its length. We already found out that Cn equals to 1.5 units in its length. So in the next step, we'll copy the right triangle CON in a new page, and we will implement the Pythagoras theorem of this right triangle, triangle CON. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Side ON of the right triangle ONC equals to 1 unit in its length. It is the radius of the small circle. Here by PT is the relation for Pythagoras theorem. So clearly this is the right triangle CON, that the common from the original domain. According to the Pythagoras theorem, in this right triangle CON, OC squared, that is the square of the hypotenuse, equals to ON squared plus NC squared. So I write it down. OC squared, that is the square of the hypotenuse, equals to ON squared plus CN squared. The hypotenuse OC equals to 2.5 units in its length, therefore OC squared is 2.5 squared, that is 6.25, and it is equals to ON squared. ON is y, therefore ON squared is y squared plus CN squared. CN is 1.5, therefore CN squared is 1.5 squared, that is 2.25. So in total we should find out that 6.25 equals to y squared plus 2.25. Here we subtract 2.25 from this equation, and finally get that 6.25 minus 2.25 is 4, equals to y squared. Here we take a look out of this equation, and finally get that y equals to the square root of 4, that is 2. So if you found out that the radius y of the small circle is equal to 2 units. The radius of this small circle, y equals to 2 units in its length. We have already found out that x minus y equals to 2.5. We also right now found out that y equals to 2. Therefore x minus y is x minus 2 equals to 2.5. Here we add 2 to this equation, and finally get that x equals to 2 plus 2.5 is 4.5. 4.5 is 9 over 2. So if you found out that the radius x of the big semicircle, it is equals to either 4.5 units in its length or 9 over 2 units in its length. Our task is to find out the area of this green shape. So what is the area of the green shape? From the drawing, it is very easy to see that the area of the green shape equals to the area of the semicircle minus the area of the circle. So I write it down. The area of the green shape equals to the area of the big semicircle minus the area of the small circle. The area of the big semicircle equals to the area of the circle squared. the radius of the semicircle is x, therefore the area of the circle must be equal to pi x squared, and the area of the semicircle must be equal to pi x squared over 2. The area of the semicircle must be equal to pi x squared over 2. Minus the area of the small circle. The radius of this small circle is y, therefore the area of the small circle must be equal to pi y squared. X is 9 over 2, therefore x squared must be equal to 9 over 2 squared. So pi x squared over 2 is pi over 2 times 9 over 2 squared minus pi y squared. Y is 2, therefore y squared is 2 squared, that is y, so pi y squared is 4 pi. So if we found out that the area of the green shape in total equals to pi over 2 times 9 over 2 squared minus 4 pi. We'll open the brackets of this expression and get that the area of the green shape in total equals to pi over 2. 9 over 2 squared equals to 9 squared, that is 81, over 2 squared, that is 4. Minus 4 pi. So we have here 81 pi over 2 times 4 is 8. So 81 pi over 8 minus 4 pi. Here we will multiply 4 pi, we multiply minus 4 pi by 8, and then we divide it by 8 in order to come comfortable with this expression, and we get it minus 4 pi over 8 is minus 32 pi over 8. 81 pi minus 32 pi equals to 49 pi over 8. 49 pi over 8 is 19.24 square units in its size. So if you found out that in total, the area of this green shape, that is the area that we are looking for in this question, it is equals to either 49 pi over 8 square units in its size, or in terms of numbers, the area of this green shape is equals to 19.24 square units in its size. So we finish with the first question. In the next step, I will present to you the second question, and we will answer on the second question of this lecture. Our task in the second question is to find out the length of this line segment PQ that equals to x. We have to find out the value of x. So in the drawing we have a semicircle. Point O is the center of this semicircle. This is line segment OS that equals to 4 units in its length. This is line segment ASB that equals to 1 unit in its length. This is angle PQB. This is a right angle. This is angle PTS, that is also a right angle. We also know that PT equals to TS. Again, our task was to find out the length of this line segment PQ that is equals to x. We have to find out the value of x. So first of all, we will complete the semicircle to a circle. And we will extend line segment TS by straight line until it touches the circle. We define the touching point of the extended line segment TS with this circle. This point is point M. In the next step, we join points P and M together by a straight line. By doing all those constructions, we actually created here peripheral PTM. This is peripheral PTM. According to what is given as the question, the size of peripheral PTM is equals to 90 degrees in its size. And peripheral PTM subtend on PM. Again, peripheral PTM subtend on chord PM. So here we can implement rule 5. I'll repeat quickly on rule 5. According to rule 5, any peripheral angle that is equal to 90 degrees must subtend on the diameter of the circle. In the drawing we have a circle. This is peripheral angle MAN, that is the right angle, it is equal to 90 degrees in its size. And according to this rule 5, any peripheral angle that is equal to 90 degrees in its size, like this peripheral angle MAN, must subtend on the diameter of the circle. So peripheral angle MAN must subtend on the diameter of the circle. On the diameter of the circle. And indeed, peripheral angle MAN subtend on MN, that is the diameter of the circle. So according to rule 5, any peripheral angle that is equal to 90 degrees in its size must subtend on the diameter of the circle. We can implement rule 5 in our drawing. Why? Because in our drawing we have peripheral angle PTM. Peripheral PTM equals to 90 degrees in its size. Therefore, according to rule 5, it must subtend on the diameter of the circle. Peripheral angle PTM subtend on chord PM, and therefore, according to rule 5, chord PM must be the diameter of the circle. So right now, if you found out that chord PM must be the diameter of the circle according to rule 5. It is given us the question that point O is the center of this circle, point P is the point on the circle itself, therefore OP is the radius of this circle. OB is also the radius of the circle, and OB in total equals to OS plus SB. So OB equals to OS is equal to 2 units in its length plus SB, that is 1. So in total OB equals to 2 plus 1, that is 3. So we found out that the radius of this circle is equal to 3 units in its length. OP is the radius of the circle, therefore it is equal to 3 units in its length. Likewise, OM is also the radius of the circle, therefore it is equal to 3 units in its length. the radius OM is equal to 3 units in its length. In the next step, we will do a construction. That is to say, from this point S, we will do perpendicular. In point S, we will do perpendicular on the diameter PM. Again, from point S, we will do perpendicular on the diameter PM. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We will define the touching point of the perpendicular from point S and the diameter PM. This point is point N. By doing this construction, you can do the right triangle ONS. Those two angles are defined as vertex angles, and we know that vertex angles are equal to each other. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other. So in the right small triangle ONS, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, in the upper right triangle PQO, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha, according to the sum rule that the sum of the angles in any triangle is equal to 180 degrees. It is very easy to see that the upper right triangle PQO is similar to the lower right triangle ONS according to angle similarity rule. I will explain anyway why those two right triangles are similar to each other. First of all, those two angles are both equal to alpha, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees, and therefore they are equal to each other. So if you found out that all the figures of the upper right triangle PQO are corresponding equal to all the figures of this right lower triangle ONS, and therefore those two right triangles are similar to each other according to angle similarity rule. So I write it down. We actually found out that the right upper triangle PQO is similar, this is the sum of similar to the right lower triangle ONS, according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side Sn of the small right triangle SNO over side PQ of the big right of the upper right triangle PQO is equal to side SO of the right lower triangle SON over side PO of the upper right triangle POQ. I repeat again, from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side SN of the lower right triangle ONS over side PQ of the upper right triangle PQO is equal to side OS of the lower right triangle ONS over side PO of the upper right triangle PQO. This is side NS. Side NS is the missing side, so we leave it as it is over PQ. PQ is the line segment that we are looking for in this question, and it is equal to x. We have to find out the value of x. And it is equal to SO according to what is given in the question. SO equals to 2 units in its length over PO. PO is the radius of this circle, it is equals to 3 units in its length. So in total, we should find out that Sn over x equals to 2/3. Here we will multiply this equation by x, and finally we get that the missing side Sn equals to 2/3 x. This is the missing side Sn that equals to 2/3 x. So write it down, Sn equals to 2/3 x. In the next step, we define this angle as beta. So in the small right triangle NSM, this angle equals to beta. This angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus beta. Why? Because 90 degrees minus beta plus beta is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in any triangle. The next step we will focus on the big right triangle PTM. On this big right triangle PTM, this angle equals to beta. Therefore, angle beta is the common angle that belongs to both triangles. So this angle equals to beta, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus beta, according to the sum rule that the sum of the angles in any triangle is equal to 180 degrees. It is very easy to see that the big right triangle PTM is similar to this small right green triangle SNM. I will explain anyway why the big right triangle PTM is similar to this small green right triangle NSM. First of all, this is angle beta, that is a common angle that belongs to both triangles. So I can write down that angle beta equals to itself is a common angle that belongs to both triangles. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. If those two angles are both equal to 90 degrees minus beta, therefore they are equal to each other. So if you found out that all the three angles of this big right triangle PTM are corresponding equal to all the three angles of this right small green triangle, triangle NSM, and therefore those two right triangles are similar to each other according to angle similarity rule. So I write it down. If you found out that the big right triangle PTM is similar, this is the sign of similar, to the right small green triangle, triangle NSM, according to angle similarity rule. And for the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side SN of the small right green triangle, triangle SNM, over side PT of the big right triangle PTM is equal to side SM of the green right triangle SNM over side PM of the big right triangle PTM. Before I continue, this gives us the question that PT equals to TS. So if we define the length of line segment PT as A, then the length of this line segment TS must be also equal to A because they are equal to each other. So if you found out that from the fact that the right big triangle PTM is similar to this green small triangle SNM, the following relationship exists between their sides. The relationship is as follows. Side SN of the right green small triangle MSN or side PT of the big right triangle PTM is equal to side SM of the small right green triangle MSN over side PM of the big right triangle PTM. We have already found out that NS or SN equals to 2/3 x. So SN is equals to 2/3 x over PT. According to our definition, PT equals to A units in its length, and it is equals to SM. SM is the missing side, so we leave it as it is, over PM. PM is the diameter of this circle. The radius is 3, therefore the diameter must be equal to 6. So PM equals to 6. So in total, we actually found out that two-thirds x over A equals to ms over 6. Here we will cross multiply this equation, and we'll get that six times 2/3 x over 6 times 2/3 x equals to A times SM. After it was multiplied, this equation, we actually found out that 6 times 2 third x equals to 8 times Sm. 6 over 3 is 2, and 2 times 2x is 4x. So in total, this side of this equation 1, we have 4x. So according to equation 1, we actually found out that 4x equals to 8 times Sm. So we can implement here rule 15. Repeat quickly on rule 15. According to rule 15, if chord AB intersects with chord CD at point O, then AO times OB equals to CO times OD. In the domain we have a circle, and we have chord AB that intersects with chord CD at point O. And according to rule 15, the following equation is true. In this domain, the following equation is true. That AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. So we can actually implement rule 15 in our domain. Why? Because in our domain we have chord TM that intersects with chord AB at point S. Again, in our domain, chord TM intersects with chord AB at point S. So all the requirements of rule 15 are satisfied, and therefore we can implement here rule 15. So at the moment we found out that in our original domain, chord TM intersects with chord AB at point S. Point S is the intersection point of chord TM with chord AB. So according to rule 15, the following equation will be true. TS times SM equals to AS times SB. So repeat again. Because of the fact that in our domain chord TM intersects with chord AB at point S, the following equation will be true. TS times SM equals to AS times SB, according to rule 15, of course. TS equals to A units in its length, according to our definition, times SM. SM is the missing side, so we leave it as it is. This will be equation 2. So in this side of the equation 2 we have A times SM, and it is equals to AS. What is the length of AS? AS in total equals to AO. That is the radius of this circle, that equals to 3, plus OS. OS equals to 2 units in its length, according to what is given in the question. So in total, AS equals to 3 plus 2, that is 5. AS is 5 times SB. SB equals to y units in its length according to what is given as the question. So in total we found out that according to equation 2, A times SM equals to 5 times 1, that is 5. So according to equation 2, A times SM equals to 5. This is according to equation 2. Well, according to equation 1, we already found out that according to equation 1, we already found out that A times SM equals to 4x. Repeat again. According to equation 1, we already found out that A times SM equals to 4x. So write it down here. According to equation 1, A times SM equals to 4x. So we have two different equations for ASM. Therefore, we get equation 3 that says that A times SM according to equation 1 must be equal to A times SM according to equation 2. And again, according equation 3 says that A times SM according to equation 1 must be equal to A times SM according to equation 2. A times SM according to equation 1 equals to 4x, and it must be equal to A times SM according to equation 2. A times SM according to equation 2 equals to 5. So in total, according to equation 3, we actually found out that 4x equals to 5. Here we will divide this equation 3 by 4 and find that according to equation 3, x equals to either 5 quarters or 1.25 units in its length. So the answer to the question is that the length of this line segment PQ is equals to x. It is equal to either 5 quarters units in its length, or in terms of numbers, it is equal to 1.25 units in its length. And that is the answer to the second question. So in the next step, of some other lecture, we'll start with the first question, of course. Our task in the first question was to find out the area of this green shape. So in the drawing we have a circle inside this big semicircle. It is given us in the question that line segment AQ equals to 4 units in its length. This is line segment TB, this is equals to 1 unit in its length. This is angle STB, this is a right angle. This is angle PQA, this is also a right angle. Again, our task is to find out the area of this ring shape. So first of all, we define the radius of this big semicircle as x, and the radius of this small circle as y. In addition, we define the center of this small circle. This point is point O, and define the radius of this big semicircle. This point is point C. AB is the diameter of the semicircle. The radius is x, therefore the diameter AB must be equal to 2x. So AB equals to 2x. In the next step, we define the point of tendency of tangent AB with this small circle. This point is point N. In addition, we define the point of tendency of tangent ST with this small circle. This point is point L. We define the point of tendency of tangent PQ with this small circle. This point is point H. And finally, we define the tangent point of this small circle with this big semicircle. This point is point K. In the next step, we join points O and N together by straight line. Point O is the center of the circle, the small circle. Point N is the point on the small circle itself. Therefore, ON is the radius of this small circle that is equal to y units in itself according to our definition. The radius ON that is equal to y, the radius ON is drawn to point N, that is the point of tendency of tangent AB with this small circle. And whenever your radius is drawn to the point of tendency, then tangent AB will be perpendicular to the radius NO. If AB is perpendicular to NO, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule 1. According to what is given in the question, this is angle PQA, this is a right angle. AB is the diameter of the semicircle, it is absolutely a straight line. So if we focus on the upper side of the straight line AB at point Q, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of AB of this, which angles we have at the upper side of the straight line AB at point Q? We have this angle that is a right angle according to what is given as the question, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we join points O and H together by straight line. OH is of course the radius of this circle, of the small circle, is equals to y. The radius OH is drawn to point H, that is the point of tendency of tangent PQ with this small circle. And whenever your radius is drawn to the point of tendency, then tangent PQ will be perpendicular to the radius HO. If PQ is perpendicular to HO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the same rule, rule 1. So inside quadrilateral HO and Q, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total it must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this fourth missing angle must be equal to 90 degrees in its side. So inside quadrilateral H, O, and Q, we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be a rectangle if not a square. So we relate to the small quadrilateral HO NQ is a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So an rectangle HO NQ side HO must be equal to the opposite side NQ. But HO is y, therefore the opposite side NQ must be also equal to y units in its length. Repeat it on the same process on this side of the drawing. It is given us the question that angle STB is a right angle. So if we focus on the upper side of the straight line AB at point T, here the sum of the angles must be equal to 180 degrees according to rule 3. For which angles we have at the upper side of the straight line AB at point T, we have this angle that is a right angle, plus this missing angle. In total, they must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. We join points O and L together by straight line. OL is of course the radius of the small circle that is y. The radius OL that is equal to y. The radius OL is drawn to point L. That is the point of tendency obtained at ST with this small circle. And now you have radius that is drawn to the point of tendency, then tangent ST will be perpendicular to the radius LO. If ST is perpendicular to LO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. So if we found out that in total, inside the quadrangle OLTN, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this 4th missing angle, in total must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrangle is equal to 360 degrees, and therefore this 4th missing angle must be equal to 90 degrees in its size. So inside quadrangle OSTN we have 4 right angles, and according to rule 5, any quadrangle that has 4 right angles must be at its rectangle if not a square. So we went to quadrangle OSTN as a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So rectangle OLTN side OL must be equal to the opposite side TN. But OL is y, therefore the opposite side TN must be also equal to y units in its length. This is line segment QT. Line segment QT is part of the straight line AB. And therefore, line segment QT must be also a straight line. Therefore, QT in total must be equal to QN plus NT. So QT in total equals to QN that is y plus NT that is y. Y plus y is 2y. So in total, QT equals to 2y units in its length. We know that AB is the diameter of the semicircle. It equals to 2x from one side. AB equals to 2x, but from the other side, AB also equals to AQ plus QT plus TB. And again, from the other side, AB also equals to AQ plus QT plus TB. AQ is 4, TB is 2y, and again AQ is 4, QT is 2y, and TB is 1. But again AQ is 4, TB is 2y, and TB is, again AQ is 4, QT is 2y, and TB is 1. So in total 2x equals to 4 plus 1, that is 5, plus 2y. So 2x equals to 2y plus 5. Again, 2x equals to 2y plus 5. Here we subtract 2y from this equation and find out that 2x times 2y equals to 5. Here we took 2 as a common factor from those two expressions, so inside the brackets we left only with x minus y, so 2 times x minus y equals to 5. Here we divided this equation by 2 and found out that x minus y equals to 5 over 2. 5 over 2 is 2.5. So in total we found out that x minus y equals to 2.5. What is the length of this missing line segment CN? From the drawing it is very easy to see that CN in total equals to CB minus NT minus TB. Again, CN in total equals to CB minus NT minus TB. And again, from the drawing it is very easy to see that CN in total equals to CB minus NT minus TB. So CN in total equals to CB. CB is the radius of the semicircle that equals to x. minus nt. Nt is y and tb is 1. So in total, Cn equals to Cb that is x minus nt that is y minus tb that is 1. So in total, Cn equals to x minus y minus 1. X minus y is 2.5. So we substitute x minus y by 2.5 minus 1. 2.5 minus 1 is 1.5. So in total, we found out that the length of the short answer at Cn is 1.5 minutes. This is 97 Cn, that is equal to 1.5 minutes in its length. Okay. So here, because of the fact that we have an eternal knot between the small circle and the big semicircle at point K, we can implement here rule 9. So if it's quickly on rule 9, according to rule 9, if two circles touch each other internally, like in our drawing, then the straight line that connects their centers together passes through their touching point. In the drawing we have two circles. The center of this big circle is 0.0. The center of this small circle is 0.m. The straight line that connects their centers together is of course the straight line OM. The straight line OM must pass through their touching point, that is point P. Again, according to this rule 9, the straight line OM must pass through point P, that is their touching point. So, or OMP is one straight line. Again, according to this rule 9, OMP is one straight line. So we can implement rule 9 in our drawing. Why? Because in our drawing, we have internal knot between the small circle and the big semicircle at point K. Therefore, we can implement here rule 9. According to rule 9, we have the center of this big semicircle is at point C. The center of this small circle is at point O. The straight line that connects their centers together is of course the straight line CO. And according to rule 9, the straight line CO must pass through their touching point, that is point K. Again, the straight line CO must pass through point K, that is their touching point. Or COK is one straight line. Again, COK is one straight line according to rule 9. If COK is one straight line, it means that COK is one straight line, therefore CO must be equal to CK minus OK. Again, CO must be equal to CK minus OK. CO equals to CK minus OK. So CO equals to CK. CK is the radius of the semicircle that is X. Minus OK. OK is the radius of the small circle that is Y. So in total, CO equals to X minus Y. CO equals to X minus Y. But we have already found out that X minus Y equals to 2.5. Therefore, CO equals to 2.5. Cn equals to 1.5 and On equals to Y. In the next step, I copied the right triangle O and C in a new page and implemented the Pythagoras theorem on this right triangle O and C. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So actually, this is the right triangle CON that according to the original drawing. In this right triangle CON, this right triangle OCN, according to the Pythagoras theorem, OC squared, that is the square of the hypotenuse, must be equal to ON squared plus NC squared. OC is 2.5, therefore OC squared is 2.5 squared, that is 6.25, and it is equal to ON squared. ON is y, therefore ON squared is y squared, plus Cn squared. Cn is 1.5, therefore Cn squared is 1.5 squared, that is 2.25. So in total, we found out that 6.25 equals to y squared plus 2.25. Here we subtracted 2.25 from this equation and finally found out that 6.25 minus 2.25 is 4 equals to y squared. Here we took out of this equation and finally found out that y equals to the square root of 4, that is 2. So we found out that the radius y of the small circle equals to 2 units in its length. We already found out that x minus y equals to 2.5, but y is 2, so x minus y is x minus 2, that equals to 2.5. Here we added 2 to this equation, and finally found out that x equals to 2 plus 2.5, that is 4.5. 4.5 is 9 over 2. Our test is to find out the area of this green shape. So what is the area of the green shape? The area of the green shape equals to the area of the big semicircle minus the area of the small circle. Okay, again, the area of the shape in total equals to the area of the big semicircle minus the area of the small circle. The area of the semicircle equals to the area of the circle over 2. The radius of the circle is x, therefore the area is pi x squared. and the area of the circle must be equal to, of the semicircle must be equal to pi x squared over 2. Now the area of the circle, the radius of the circle is y, therefore the area of the circle must be equal to pi times the radius squared, that is pi times y squared. X is 9 over 2, therefore x squared is 9 over 2 squared, so in total this expression equals to pi over 2 times 9 over 2 squared minus pi times y squared. Y is 2, therefore y squared is 2 squared, that is 4, so in total this expression equals to 4 pi. We open the brackets on this side, we open the brackets of this expression, and found out that this expression equals to pi over 2 times 9 over 2 squared. 9 over 2 squared is equals to 9 squared, that is 81, over 2 squared, that is 4. So in total this expression equals to 81 pi over 2 times 4 minus 4 pi. So it is 81 pi and 2 times 4, that is 8. So in total this expression equals to 81 pi over 8 minus 4 pi. We multiplied minus 4 pi by 8 and then we divided by 8 in order to account for of this expression. So minus 4 pi times 8 is minus 42 pi divided by 8. 81 pi minus 42 pi is 49 pi divided by 8. So in total if you found out that the area that we are looking for in this question, that is there of this green shape, it is equals to either 49 pi over 8 square units in its size, or in terms of numbers, the area of this green shape equals to 19.24 square units in its size. So we finish with the first question. In the next step we are presented to do the second question, and we solve the second question of this lecture. In the second question, our task is to find out the length of this line segment PQ that equals to x. We have to find out the value of x. In the drawing, we have a semicircle. We know that point O is the center of the semicircle. This is line segment OS, that is equals to 2 units in its length. This is line segment SB, that is equals to 1 unit in its length. This is angle PQS, that is a right angle. This is angle PTS, that is also a right angle. Again, our task is to find out the length of this line segment PQ, that is equals to x. We have to find out the value of x. So first of all, we completed the semicircle to a circle. We extended line segment PS by straight line until it touches the circle. At this point, we define the touching point of the extended line segment TS with this circle. This point is point M. In the next step, we join points P and M together by straight line. When doing all those constructions, we can do peripheral PTM. Peripheral PTM is equal to 90 degrees in size according to what is the question, and peripheral angle PTM subtend on chord PM. Again, peripheral angle PTM subtend on chord PM. And according to all 5, any peripheral angle that is equal to 90 degrees in size, exactly like this angle, must subtend on the diameter of the circle. So because of the fact that peripheral angle PTM is a right angle, it must subtend on the diameter of the circle. Peripheral angle PTM subtend on chord PM, and therefore chord PM must be the diameter of the circle according to all 5. Okay, so point O is the center of the circle. Point B is the point of the circle itself, so for OB is the radius of the circle. OB in total equals to OS, that is 2, plus SB, that is 1. So in total, the radius OB equals to 2 plus 1, that is 3. OP is also the radius, that is 3. OM is also the radius, that is 3. In the next step, we did the construction, that is to say from point S, we do perpendicular on the diameter PM. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point S and the diameter PM. This point is point N. When doing this construction, we added the right triangle S and O. Those two angles are defined as vertex angles, and we know that vertex angles are equal to each other. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other. So in the right small triangle O and S, this angle equals to alpha. This angle equals to 90 degrees minus alpha, therefore this angle equals to alpha. This angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equals to 180 degrees. That is the sum of the angles in the triangle. Likewise, in this upper right triangle PQO, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first angle must be equal to 90 degrees minus alpha, according to the sum rule that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we prove that the right upper triangle PQO is similar to the right lower triangle SNO. So right, those two right triangles are similar to each other. First of all, those two angles are both equal to alpha, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So if we found out that all the figures of the of the upper right triangle PQO correspond equal to all the figures of the right lower triangle OSN. And therefore those two right triangles are similar to each other according to angle similarity rule. If we found out that the upper right triangle PQO is similar, this is the sign of similar to the lower right triangle ONS according to angle similarity rule. And from the fact that those two right triangles are similar to each other, the following relationship exists between their sides. Side CN of the right triangle ONS, again side SN of the lower right triangle ONS, over side PQ of the upper right triangle PQO is equal to side SO of the right lower triangle OSN over side PO of the upper right triangle PQO. Okay, SN over PQ equals to SO over PO. SN is the missing side, so we leave it as it is. PQ is this. SO equals to 2 units in itself, or PO. PO is 3. So in total, we found out that SN over X equals to 2/3. Here we multiply this equation by X and we found out that the missing side SN equals to 2/3 X. SN equals to 2/3 X. This is the missing side SN, is equals to 2/3 X. In the next step, we define this angle as beta. So in the right triangle SNM, this angle equals to beta. This angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus beta. Why? Because 90 degrees minus beta plus beta is 90 degrees, and 90 degrees plus 90 degrees is equals to 180 degrees. That is the sum of the angles in the triangle. Likewise, in the big right triangle PTM, this angle is beta. Therefore, angle beta is the common angle that belongs to both angles. So this angle equals to beta, this angle equals to 90 degrees. Therefore, this first missing angle must be equal to 90 degrees minus beta according to the sum rule that the sum of the angles in the triangle is equal to 180 degrees. In the next step, we prove that the big right triangle PTM is similar to this main right triangle SNM. Why those two right triangles are similar to each other? First of all, this is the angle beta, that is a common angle that belongs to both angles. So we can find out that angle beta equals to itself as a common angle that belongs to both angles. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus beta and therefore they are equal to each other. So if you prove that all the figures of the big right triangle PTM correspond equal to all the figures of this right small triangle SNM. And therefore those two right triangles are similar to each other according to angle similarity rule. Again, if you found out that the big right triangle PTM is similar to the right small triangle NSM according to angle similarity rule. From the fact that the big right triangle PTM is similar to the green triangle, we derive that the following relationship exists between their sides. We derive the side SN of the green triangle over side PT of the big right triangle PTM is equal to side SM of the green triangle over side PM of the big right triangle PTM. Again, we derive that SN over PT equals to SM over PM. SN is 2/3 X, PT is A, SM is the missing side, so we leave it as it is, and PM is the diameter of the circle, that is 6. So in total, 2/3 X, we found out that 2/3 X over A equals to SM over 6. Here we can multiply this equation, and finally found out that 6 times 2/3 X equals to ASM. 6 over 3 is 2, and 2 times 2x is 4x. So in total, this side of the equation 1, we have 4x equals to ASM. We can implement in our drawing rule 15. Rule 15. According to rule 15, if chord AB intersects with chord CD at point O, then the following equation is true, that AO times OB equals to CO times OD. In the drawing, we have a circle, and this is called AB that intersects with chord CD at point O. In this drawing, the following equation is true, that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. So we can actually implement all 15 in our drawing. Why? Because in our drawing we have code TM, that is the section code TM, the section code AB at point S. So all the requirements for full 15 are satisfied, and therefore we can implement all 15. And again, in our drawing, code TM, the section code AB at point S. And therefore the following equation will be true, that TS times SM equals to AS times SB. Again, TS times SM equals to AS times SB according to all 15. TS is A, according to our definition, over SM. SM is the missing sign, so we know it as it is, and it is equals to AS. AS in total equals to 3 plus 2, that is 5, times SB. SB is 1. So in total we should find out that A times SM equals to 5 times 1, that is 5. So A times SM equals to 5 according to equation 2. But according to equation 1, we should find out that A times SM equals to 4x. So we have two different equations for ASM, therefore we created equation 3 that states that ASM according to equation 1 must be equal to ASM according to equation 2. ASM according to equation 1 is 4x, and it must be equal to ASM according to equation 2. ASM according to equation 2 is 5. So in total, according to equation 3, we have found out that 4x equals to 5. Here we divided this equation 3 by 4, and finally found out that x equals to 5 quarters. 5 quarters is 1.25. So we should find out that the length of this short line segment PQ is equal to x. It is equal to either 5 quarters units in its length, or in terms of numbers, it is equal to 1.25 units in its length. Okay, thank you very much.